Hello everyone, welcome to Easy Maths. In this tutorial we are going to learn about differentiation. So most of the people raise this question that why is it important to learn about differentiation? Let me start with a story. During Sir Isaac Newton's days, one of the biggest problems was the poor navigation at sea. Because of that, shipwrecks occurred and the ships were not where the captains thought they should be. There was not enough understanding of how the Earth, stars and planets moved with respect to each other. So once the calculus was developed, navigation was better understood by scientists and captains of the ships. Also, calculus can help us to solve many types of real-world problems, such as to find the rates of change and problems related to distance, velocity and acceleration. Acceleration is the derivative of velocity, which in turn is the derivative of the displacement. We use the derivative to determine the maximum and minimum values of particular functions. For example, cost, strength, amount of materials used in a building, profit and loss can be found using the derivative of functions. Derivatives are also met in many engineering and science problems, especially when modeling the behavior of moving objects. So we are going to learn about tangent and normal, gradient of a curve and gradient of a function. Tangents and normals. If A and B are 2 points on a curve, that can be any curve, then the line joining A and B is called a chord. The line touching the curve at A is called the tangent to the curve at A. And the line which is perpendicular to the tangent at A is called the normal to the curve at A. So if you look at this diagram, the line AB is the chord of the curve. And the line which goes through A, which is over here, is called the tangent, and the line which is perpendicular to the tangent is called as the normal. Gradient of a curve. The gradient of a curve, which is a measure of its slope, changes continually as one moves along it. Suppose when moving along the curve in the diagram, so in the sense B tends to A, that at the point A, the gradient stops changing and remains constant. One would then move along the straight line AT, that is along the tangent at curve. So if you look at this diagram over here, AB is the chord and AT is the tangent. We can find the gradient of a curve by the rate of increase of y with respect to x. So we can take any 2 points on the curve and find the gradient. So if we consider 2 points like A and B moves towards A. So when the B moves towards the A, the B changes its position. So once it reaches A, the B becomes A. So the gradient of the curve at the point A is the same as the gradient of the tangent at A. So we can say the gradient of a curve at any point is defined as the gradient of the tangent to the curve at that point and measures the rate of increase of y with respect to x. An approximate value for the gradient of a curve at a point can be found by plotting the curve, drawing the tangent by I and measuring its gradient. This method has to be used for a curve when the coordinates of a finite number of points are known, but its equation is not. When the equation of a curve is known, an accurate method of determining gradient is necessary so that we can further our analysis of curves and functions. So there are two diagrams given and we are going to discuss how the gradient of a chord AB equals to gradient of a tangent AT. So consider first the problem of finding the gradient of a curve at a point A. If B is another point on the curve which is not too far from A, then evaluating the gradient of the chord AB gives us an approximate value for the gradient of the tangent at A. So the closer B is to A, the better is the approximation. So as the b moves along the curve towards the a, we get a better approximation. And once it reaches a, so we can say the gradient of chord AB tends to gradient of tangent AD. Or limit of b tends to a, where gradient of chord AB equals to gradient of tangent AD. So like what we discussed before, when b tends to a, the gradient of the chord AB becomes the gradient of tangent AD. The delta prefix, a variable quantity prefixed by delta x, is a small increase in x. Delta y is a small increase in y, and delta v is a small increase in v. Note that delta is only a prefix. It cannot be treated as a factor. If delta x is the increase in the x coordinate in moving from a to b, then x coordinate of b is 1 at delta x. For all points of the curve, y equals x bracket 2x take away 1. So at a, x equals 1, and by substituting x equals 1 in the equation y equals x bracket 2x take away 1, we can get the coordinates of y at a, which is y equals 1. And as there is an increment of delta x at point b, we get the coordinate of x as 1 at delta x, and by substituting 1 at delta x in the equation y equals x bracket 2x take away 1, we get the coordinate of y, which is 1 at delta x bracket 2 bracket 1 plus delta x take away 1. So by simplifying the expression, we get 1 plus delta x bracket 2 delta x plus 1. So if you look at the graph of y equals x bracket 2x take away 1, so a and b are marked on the graph, and the gradient of the chord AB is what we need to find out. So the gradient of chord AB, which is the increase in y over increase in x, to find the increase in y, we need to take away the y coordinate of a from the y coordinate of b, which is 1 at delta x bracket 2 delta x plus 1 take away 1. And the denominator is what we get as the x coordinate of a taken away from the x coordinate of b, so which is 1 at delta x take away 1. By simplifying the expression, we get 2 delta x whole thing square plus 3 delta x over delta x. By dividing the top and the bottom expressions by delta x, we can get 2 delta x plus 3. So as b approaches a, the difference between their x coordinates approaches 0. So that is delta x tends to 0. As delta x tends to 0, in the expression 2 delta x plus 3, the 2 delta x gets 0, and the answer for gradient at a would be just 3. So we represent it as gradient at a equals limit of gradient of chord AB, where b tends to a. So when b tends to a, the delta x becomes 0, which means delta x tends to 0. So as a result, the gradient at a becomes 3. Now pause the video and try this question by yourself. How did that go? Example 1a. Using the method described above, find the gradient of the curve y equals 1 over x at the point where x equals 2. So we are going to use the same method like what we have done before. So the solution is delta x be the increase in moving from a 2, 1/2 to a near point b on this curve, so that the coordinates of b are 2 plus delta x, 1 over 2 plus delta x. So here we get the coordinates of b as 2 plus delta x and 1 over 2 plus delta x, because we are substituting 2 plus delta x in the equation y equals 1 over x, and there's an increment of delta x. the gradient of chord AB equals the increase in y over the increase in x. So the increase in y equals 1 over 2 plus delta x take away 1 half over the increase in x, which is delta x. Those two gets cancelled off, so the result would be delta x. So by simplifying, the gradient of chord AB becomes negative delta x over 2 delta x bracket 2 plus delta x. And by dividing the top and the bottom by delta x, the answer becomes negative 1 over 2 bracket 2 plus delta x. By taking off the brackets in the denominator, we get 4 plus 2 delta x as the denominator. Therefore, the gradient at A equals limit of negative 1 over 4 plus 2 delta x, where delta x tends to 0. So the final answer for the gradient at A equals negative 1 over 4. So it is always better to draw a diagram like this to get a clear understanding of what we are going to do in order to find the gradient of a curve. Gradient function. Earlier in this tutorial, we found that the gradient of the curve y equals x bracket 2x take away 1 is 3 at the point on the curve where x equals 1. So we will now derive a function for the gradient at any point on the curve. Then we can find the gradient at a particular point by substitution into this derived function. Instead of taking a fixed point on the curve, we will take A as any point x comma y on the curve. Its y coordinate can then be written as x bracket 2x take away 1, since both coordinates satisfy the equation y equals x bracket 2x take away 1. Let B be another point on the curve such that the increase in the x coordinate in moving from A to B is delta x. Then B is the point x plus delta x comma x plus delta x bracket 2 x plus 2 delta x take away 1. So that is the coordinate of point B. Then, like the method which we have used before, to find the gradient of AB, we write down the increase in y over the increase in x. So x plus delta x bracket 2x plus 2 delta x take away 1, take away x bracket 2x take away 1 over delta x. So by simplifying, we get 2x square plus 4x delta x plus 2 delta x whole thing square, take away delta x, take away x, take away 2x square plus x over delta x. And then by simplifying again, we get 4x delta x take away delta x plus 2 delta x whole thing square over delta x. So by dividing the top and the bottom expressions by delta x, we get the answer for gradient of AB as 4x take away 1 plus 2 delta x. Since the delta x tends to 0 as B tends to A, we can find the gradient at any point A on the curve, which is limit of 4x take away 1 plus 2 delta x, where delta x tends to 0, get the answer 4x take away 1. So the function 4x take away 1 gives the gradient at any point on the curve y equals x bracket 2x take away 1. We can find the gradient of the curve, that is the rate of increase of y with respect to x, at a particular point on y equals x bracket 2x take away 1 by substituting the x coordinate of that point into the function 4x take away 1. Thus, 4x take away 1 is called the gradient function of y equals x bracket 2x take away 1, and the process of deriving it is called differentiation with respect to x. Now 4x take away 1 was derived from the function x bracket 2x take away 1. So 4x take away 1 is called the derivative or derived function of x bracket 2x take away 1. Using d dx as a symbol to denote derivative with respect to x of, we may write d dx of x bracket 2x take away 1 equals to 4x take away 1. Or when y equals x bracket 2x take away 1, dy by dx equals 4x take away 1, where dy by dx means the derivative of y with respect to x and is sometimes called the differential coefficient of y. As an alternative notation, we can use the symbol d for derivative or derived function of, that is, d of x bracket 2x take away 1 equals 4x take away 1, where d is referred to as the differential operator. Now 4x take away 1 represents the rate of increase of y with respect to x. Therefore dy by dx represents also the rate of increase of y with respect to x. Similarly, dv by dt means the derivative of v with respect to t, or the rate of increase of v with respect to t, etc. So dv by dt is used when we deal with the differential equations for velocities. So v represents velocity and t represents the time. So by finding the derivative of v with respect to t, we find the acceleration of the motion. Now take some time and work on this question by yourself. Example 1b. Differentiate y equals x cubed plus 3 with respect to x. So the solution is a be the point x comma x cubed plus 3 and b be the point x plus delta x comma x plus delta x whole thing cubed plus 3 on y equals x cubed plus 3. So we are taking a and b as 2 points on the curve of y equals x cubed plus 3. And as we need to find out the common expression for the gradient of AB, we are taking the point A as x comma x cubed plus 3, and we are substituting x plus delta x in the equation y equals x cubed plus 3 to get the coordinates of B. So the gradient of AB equals the increasing y over the increasing x, which is x plus delta x whole thing cubed plus 3 take away x cubed plus 3 over delta x, which simplifies to 3x square plus 3x delta x plus delta x whole thing square. So the gradient at A equals limit of 3x square plus 3x delta x plus delta x whole thing square, where delta x tends to 0. So as delta x tends to 0, we get an answer as 3x square. So we can say dy by dx, or derivative of y with respect to x, equals 3x squared.
Hello everyone, welcome to Easy Maths. So in our previous part of tutorial about differentiation, we learned about tangents and normals, and also we learned to calculate the gradients of curves and functions. We figured out that the gradient of a curve at any point is defined as the gradient of the tangent to the curve at that point and measures the rate of increase of y with respect to x. We also learned that when b goes to a, the limit of gradient of chord AB equals to gradient of tangent AT. So in this tutorial, we are going to learn about general differentiation and equations of tangents and normals. Under general differentiation, we are going to find out the differentiation of a constant, differentiation of ax where a is a constant, differentiation of x to the power n, and differentiation of ax to the power n. General differentiation. Consider any curve y equals f of x. So the curve is shown in this diagram. Let a, x comma f of x be any point on y equals f of x. Let delta x be the increase in the x coordinate in moving from a to another point b on the same curve. So b is the point x plus delta x comma f of x plus delta x. Let delta y be the corresponding increase in the y coordinate in moving from a to b. That is, delta y equals f of x plus delta x take away f of x. So if you look at this diagram, AB is any chord, such that A has x comma f of x and B has x plus delta x and f of x plus delta x. Delta x is the increment in the x coordinate and delta y is the corresponding increment in the y coordinate. So the gradient of AB equals the increase in y over increase in x, which equals to delta y over delta x. So delta y equals f of x plus delta x take away f of x over delta x. Therefore, the gradient at A is limit of delta y over delta x where delta x goes to 0 equals limit of f of x plus delta x take away f of x over delta x where delta x goes to 0. So we know that the gradient of any curve is given by dy by dx. That is limit of delta y over delta x where delta x goes to 0. Or we can say differentiation of f of x with respect to x equals limit of f of x plus delta x take away f of x over delta x. This formal definition of differentiation can be used to differentiate any function that have not yet met. This process is called differentiating from first principles. Fortunately, it is not always necessary to go back to first principles because certain categories of function can be differentiated by rules, some of which we will now find. Which means we don't need to go with the first principles all the time. We can use some of the rules for differentiation. So the first rule is differentiation of a constant. Consider the equation y equals c. This represents a straight line parallel to the x-axis and so it has zero gradient. Since the curve is y equals to c, it cuts the y-axis at x equals 0 and also it has a gradient of 0. So dy by dx equals 0, or we can say derivative of c with respect to x equals 0. So any constant differentiated with respect to x equals 0. Differentiation of ax where a is a constant. Consider the equation y equals ax. This represents a straight line with gradient a. That is dy by dx equals a, or derivative of ax with respect to x equals a. So the next rule of differentiation is differentiation of x to the power n. The table below summarizes the results for some of the questions in exercise 1b, which we had in our differentiation part 1 tutorial. So if you look at the table, f of x and derivative of the f of x with respect to x is given. X squared would give us 2x, x cubed would give us 3x squared, x to the power 4 gives us 4x cubed, and x to the power negative 2, which equals to 1 over x squared, equals negative 2x to the power negative 3. From the table, it appears that to differentiate a power of x, we multiply by the power and then subtract 1 from the power. That is, derivative of x to the power n with respect to x gives us n x to the power n take away 1, which is equation 1. This result deduced from a few examples is in fact valid for all powers of x, including fractional and negative powers. Although proof is not possible at this stage, this is one example of many such rules whose validity for the time being we must take on trust. So the rule number 1 can be used for any powers including fractional and negative powers. Accepting that rule 1 above can be used for any power of x, the following examples illustrate its application. Example. So derivative of x to the power 9 with respect to x equals 9x to the power 8. Derivative of x to the power negative 4 with respect to x gives negative 4 times x to the power negative 4 take away 1, which gives us negative 4x to the power negative 5. Derivative of root of x with respect to x equals derivative of x to the power 1 half with respect to x. So when we derive x to the power 1 half with respect to x, we get 1 half times x to the power 1 half take away 1, which equals to 1 half times x to the power negative 1 half. So when we derive a power of x, we multiply by that power and then we subtract 1 from the power. So when you look at the example derivation of x to the power 1 half, we times by the power which is half and then we take away 1 from the power which is 1 half take away 1. So the result is 1 half times x to the power negative 1 half. So that happens for each of these examples. So we multiply by the power and then we subtract 1 from the power. Now try out these questions by yourself. Differentiate by rule the following with respect to x. So we have x to the power 5, x to the power negative 3, x to the power 1/3, 1 over root of x, and then cubic root of x squared. So if you try out these questions, you will get answers like this. So when you derive x to the power 5 with respect to x, we multiply by the power and then subtract 1 from the power. So we get 5 times x to the power 4. And when you work out differentiation of x to the power negative 3 with respect to x, so we multiply by the power which is negative 3 and then we take away 1 from the power which is negative 3 take away 1. So we get negative 3 times x to the power negative 4. Similarly, when x to the power 1/3 is derived with respect to x, we get 1/3 times x to the power 1/3 take away 1, which is 1/3 times x to the power negative 2/3. So when we work out the derivation of 1 over root x, 1 over root x can be written as x to the power negative 1 half, because root x can be written as x to the power half. So as the root x is at the denominator, when we take it to the numerator, it becomes negative 1 half. So derivation of x to the power negative 1 half gives times by the power which is negative 1 half, and then we take away 1 from the power which is negative 1 half take away 1. So we'll be getting 1 half times x to the power negative 3 halves. When cubic root of x squared is derived with respect to x, first we convert. So we get x to the power 2/3. So this is because a denominator of 3, as it is the cubic root of x squared. So the 2 comes as the numerator and the 3 comes as the denominator. So when it is differentiated, we get 2/3 times x to the power 2/3 take away 1, which would give us 2/3 times x to the power negative 1/3. So the next rule is differentiation of ax to the power n. Selecting some more results from exercise 1b, we see that derivative of 3x squared to the respect to x gives us 3 times 2x. So we multiply by the power and then we subtract 1 from the power, so which would give us 3 times 2x. Similarly, we get 5 times 3x squared for the derivation of 5x cubed with respect to x. So these results suggest that derivative of ax to the power n with respect to x gives us a times derivative of x to the power n with respect to x equals a n x to the power n take away 1. So if you look at this expression, a is a constant like 3 and 5, and x to the power n is the term which has power. So we can take the a out of the derivative and then we can derive the term with the power, so that we'll be getting a n x to the power n take away 1. So here we are getting n because of the rule where when we derive a power of x, we multiply by that power and then we take away 1 from that power. So again, selecting from exercise 1b, we have derivative of x squared plus 3x with respect to x gives us 2x and plus 3. So we can consider the derivative of each of the terms, x squared and then 3x. So when we separately derive them, we get 2x at 3. So the same way we do it for the next expression also. So when we derive x squared take away 2x plus 1 with respect to x, we get 2x take away 2. Since 1 is a constant, it becomes 0 when we derive it with respect to x, as there is no any x in the term 2. So the answer would be 2x take away 2. So this suggests that the operation differentiate is distributive across addition and subtraction of fractions. That is, differentiation of f of x plus g of x with respect to x gives us differentiation of f of x plus differentiation of g of x with respect to x. So we distribute f of x at 3 of x into 2 separate terms and then we differentiate separately. So that's why we call differentiation is distributive across addition and subtraction of fractions. But this is not true for multiplication and division. So that is the third equation which we get, which can be used in exercises. Therefore, derivative of 3x squared take away 7x with respect to x gives us 3 times 2x take away 7, which is 6x take away 7. And derivative of x plus 1 over x with respect to x gives us derivative of x plus x to the power negative 1 with respect to x, which equals to 1 take away x to the power negative 2. So we get 1 when we derive x. So as we are deriving separately, so we get differentiation of x with respect to x at differentiation of x to the power negative 1 with respect to x. So when we differentiate x with respect to x, we get 1. Since the power of x is 1 in just x, x to the power negative 1 is differentiated with respect to x. We times by the power and then we take away 1 from the power. So that would give us negative x to the power negative 2. So that's how we get 1 take away x to the power negative 2 as the answer. So note that differentiation is not distributive across multiplication and differentiation. So differentiation of x times x take away 3 with respect to x gives us differentiation of x squared take away 3x with respect to x. So we have expanded the brackets and we got x squared take away 3x. Differentiating x squared take away 3x would give us 2x take away 3. But when we distribute x and x take away 3, and when we differentiate separately, we get the derivative of x with respect to x as 1, and the derivative of x take away 3 with respect to x would give us 1. So 1 times 1 is 1, which is not equal to 2x take away 3. So that means differentiation of x times x take away 3 with respect to x is not the same as differentiation of x with respect to x times the differentiation of x take away 3 with respect to x. So in order to differentiate at this stage, therefore any product must be expanded and any quotient must be divided by how to give terms which are added or subtracted. So if we get an expression like x times x take away 3, it is better to expand the expression as x squared take away 3x and then differentiate the terms separately. Example 2D. Differentiate f of x equivalent to 4x squared plus x take away 1 over 2x. So the function of f of x is 4x squared plus x take away 1 over 2x. So by simplifying the expression, we get 4x squared over 2x at x over 2x take away 1 over 2x. So we get such an expression because 2x is the common denominator for each of the terms 4x squared, x and negative 1. So that's how we distributed the expression into separate terms. So therefore f of x becomes 2x plus 1 half take away 1 half x to the power negative 1. So we got the 2x by dividing 4x squared by 2x, and then x over 1 half would give us just 1 half because we just cancel out 1x from the top and the bottom. So we get 2x when we divide 4x squared by 2x. So 4 divided by 2 is 2, and x squared divided by x would give us x. Similarly, we divide the top term by the bottom term, which would give us 1 half. And then we take the x to the top, which is x to the power negative 1. We get the expression as 2x plus 1 half take away 1 half x to the power negative 1. Therefore, derivative of f of x would give us 2 at 0, since 1 half is a constant. Take away 1 half times negative x to the power negative 2. So we times by the power and then take away 1 from the power, so that would give us x to the power negative 2, which equals to 2 at 1 half x to the power negative 2, which is simplified to get 2 plus 1 over 2x squared. Moving on to the next question. Find the gradient of the curve y equals x take away 3 times x squared plus 2 at the point on the curve where x equals 1. So the equation y equals x take away 3 times x squared plus 2 can also be written as y equals x cubed take away 3x squared plus 2x take away 6. So when we expand the brackets, we get x cubed take away 3x squared plus 2x take away 6. So therefore, the derivative of y with respect to x would give us 3x squared take away 6x plus 2. Since there is x cubed, we times by the power and then we take away 1 from the power, which would give us 3x squared, and then take away 3 times the power would give us 6. Take away 1 from the power would give us 1, so x to the power 1. Then it becomes negative 6x plus 2 is a constant with the x term, so that we get 2 at the end. 6 is a constant without any x terms, so it becomes 0 when we derive negative 6 with respect to x. So when x equals 1, as we are asked to find the curve at x equals 1, we substitute x equals 1 in the gradient of the curve, which would give us 3 times 1 squared take away 6 times 1 plus 2. So simplifying the calculation would give us negative 1 as the answer. Therefore, the gradient of y equals x take away 3 times x squared plus 2 is negative 1 at the point where x equals 1. Find the coordinates of the point on the curve y equals 2 over x squared at which its gradient is 1/2. So we are asked to find the point on the curve where the gradient is 1/2. So y equals 2 over x squared can be written as 2 times x to the power negative 2. Since the denominator is x squared, we take it to the top. We get a negative power. So dy by dx, which is the gradient of a curve, equals negative 4x to the power negative 3. Since we times by the power and take away 1 from the power. So now we have two values for the gradient. When we equate those two values, we get negative 4x to the power negative 3 equals 1/2. And by taking the x to the power negative 3 to the denominator, we get negative 4 over x cubed equals to 1/2. By cross multiplication, we get x cubed equals negative 8. So we need to find the cubic root of negative 8, which becomes negative 2. So x equals negative 2. At the point on y equals 2 over x squared, where the gradient is 1/2, the x coordinate is negative 2, and when x equals negative 2, the y equals 1/2. Therefore, the gradient of y equals 2 over x squared is 1/2 at the point negative 2, 1/2. Exercise 2D. Differentiate with respect to x. 3x squared take away 7x. X cubed plus 2 over x. So now try out these questions by ourselves. So first we consider y equals 3x squared take away 7x. Then if we differentiate with respect to x, we get 6x take away 7. So we multiply by the power and then take away 1 from the power. And negative 7x differentiated with respect to x gives us negative 7. If you differentiate x cubed plus 2 by x with respect to x, we get, so first we consider y equals to x cubed plus 2 over x, and we distribute, and if we divide x cubed by x, we get x squared, and 2 over x can be written as 2x to the power negative 1. Then if we differentiate y with respect to x, we get 2x take away 2x to the power negative 2. So when x squared is differentiated with respect to x, so 2 is multiplied and 1 is taken away from the power. So that's how we got 2x here. Similarly, negative 1 is multiplied with the 2, so we get negative 2, and 1 is taken away from the power, which gives us x to the power negative 2. So we get 2x take away 2x to the power negative 2. And 2 is common for both the terms, so we take 2 out of the brackets. So the answer is 2 bracket x take away 1 over x squared. So x to the power negative 2 can be written as 1 over x squared. Find the gradient of the given curve at the given point on the curve. Y equals x squared take away 3, where x equals 1. So the point is where you get x equals 1. And the second question is y equals x take away 3 times x plus 4. So the point where we need to find the gradient is at x equals negative 1. So if you work out the first question, we get dy by dx equals 2x. The point is at x equals 1, so therefore dy by dx equals 2 times 1, which is 2. So we can say the gradient of the given curve is 2 at the given point where x equals 1. Similarly, when you work out the second question, we find that y equals x take away 3 times x plus 4. So we can simplify by taking off the brackets, which is x squared plus x take away 12. And by differentiating with respect to x, we get 2x plus 1. As the point is at negative 1, we substitute negative 1 instead of x in the dy by dx. So we get 2 times negative 1 plus 1, which is negative 2 plus 1 equals negative 1. Find the coordinates of the point or points on the given curve at which its gradient has the given value. So the equation of the curve is given, and we are asked to find the coordinates on the given curve at which the gradient has the given value of 1. So dy by dx equals 2x take away 1, and the given point, and the gradient has a given value of 1. So we have an expression for dy by dx, and also we have a value for dy by dx. So we equate both of them, and we get 2x take away 1 equals 1. And by bringing the 1 on this side, on the other side, we get 2x equals 2. And by dividing both the sides by 2, we get x equals 1. So at the point on y equals x squared take away x plus 3, where the gradient is 1, the x coordinate is 1, and when x equals 1, y equals 3. So we got y equals 3 because we substituted x equals 1 in the equation y equals x squared take away x plus 3. So if you substitute 1, you get 1 squared take away 1 plus 3, which equals to 3. Therefore, the gradient of y equals x squared take away x plus 3 is 1 at the point 1, 3. Y equals root of x. So the gradient value is given as 2. So y equals root of x, and root of x can be written as x to the power 1/2. So dy by dx equals 1/2 times x to the power 1/2 take away 1. Where we have done the multiplication of the power and taking away 1 from the power. So by simplifying the calculation in the power, we get 1/2 x to the power negative 1/2. And we have the dy by dx value, which is 2. So we equate the expression and the value, which is 1/2 x to the power negative half equals 2. And by multiplying both the sides by 2, we get 1 over root x equals 4. So we got 1 over root x because x to the power negative 1/2 can be written as 1 over root x. And by cross multiplication, we can get root x equals 1 over 4. As we need to find out the value for x, we need to find the square of both the sides so that we get the value of x. So x equals 1 over 4 squared, 1 over 4 whole thing square, which is x equals 1 over 16. So at the point on y equals root of x, where the gradient is 2, then the coordinate is 1 over 16. And when x equals 1 over 16, y equals 1 over 4. Therefore, the gradient of y equals root of x is 2 at the point 1 over 16, 1 over 4. Equations of tangents and normal. Now that we know how to find the gradient of a curve at a given point on the curve, we can find the equation of the tangent or normal to the curve at that point. So we know that normal is perpendicular to the tangent. So using that information, we are going to figure out the answer for these questions. So examples 2e, find the equation of the tangent to the curve y equals x squared take away 3x plus 2 at the point where it cuts the y-axis. So if the curve is cutting the y-axis, the x-coordinate of the y-axis is 0. So y equals x squared take away 3x plus 2 cuts the y-axis where x equals 0. So when we substitute x equals 0 in the equation y equals x squared take away 3x plus 2, we get 2 for y. The gradient of the tangent at 0, 2 is the value of dy by dx when x equals 0. So we got the gradient of the tangent at the point 0, 2. So that is where the curve cuts the y-axis. So as y equals x squared take away 3x plus 2, dy by dx equals 2x take away 3. When x equals 0, the gradient of the curve is negative 3. So we substitute 0 for x in the gradient of the curve, which is 2x take away 3. So we got the answer as -3 by substituting x equals 0. So therefore the tangent has gradient of -3 and passes through 0, 2. So its equation is y equals -3x plus 2. So we got the equation of the tangent as y equals -3x plus 2 because the general equation for a straight line is y equals mx plus c. So m is the gradient and c is the intercept. So we know the gradient is -3 and the intercept is 2 because the curve is cutting the y-axis at y equals 2. So that is 3x plus y take away 2 equals 0. So that's it for this tutorial. I hope you enjoyed learning about general differentiation, where we learned about differentiation of a constant, differentiation of ax, where a is a constant, differentiation of x to the power n, and differentiation of ax to the power n. So any constant differentiated with respect to x is 0, and we found when ax is differentiated with respect to x, gave us a as the power of x is 1, and the differentiation of x to the power n would give us nx to the power n take away 1, which is we multiply the power and take away 1 from the power. And the differentiation of 8x to the power n give us anx to the power n take away 1. And also we learnt about equations of tangents and normals. So we'll be giving you more questions and explanations in our upcoming tutorials, and also use the links given in the description to practice more on differentiation. So for all of that and more, I'll meet you in the next tutorial. Thank you. Hello everyone, welcome to this part of tutorial about differentiation. In the previous part we learned about general differentiation and differentiation of a constant, differentiation of ax where a is a constant, differentiation of x to the power n and ax to the power n. Also we discussed about whether the differentiation is distributive across addition and subtraction. So in this part of tutorial we are going to learn about stationary values, turning points, and investigating the nature of stationary values. A stationary value of a function f of x is any value of f of x at which its rate of change with respect to x is 0. That is, the stationary values of f of x occur when differentiation of f of x with respect to x is 0. For a graphical representation of a stationary value, consider this curve whose equation is y equals to f of x. At a stationary value of f of x, dy by dx equals to 0, which is the differentiation of y with respect to x equals to 0. So that is the gradient of the curve is 0. And also the tangent to the curve is parallel to the x-axis. Therefore, stationary values of f of x are the values of the y coordinates of points on the curve y equals f of x, at which the tangent is parallel to the x-axis. So if you consider this example, find the stationary values of x cubed, take away 3x squared plus 2. So if f of x is equivalent to x cubed take away 3x squared plus 2, then differentiation of f of x with respect to x is equivalent to 3x squared take away 6x. So at the stationary values of f of x, the differentiation of this f of x with respect to x equals to 0. So if we equate 3x squared take away 6x to 0, then by taking the x out and factorizing would give us x times bracket x take away 2 equals to 0. So that is the stationary values of x cubed take away 3x squared plus 2 occur when x equals 0 and when x equals 2. So these stationary values are f of 0 equals to 2 and f of 2 equals to 2 cubed take away 3 times 2 to the power 2 plus 2, which equals to -2. So the stationary values occur at 2 points on this curve, which are 0, 2 and 2, -2. So as the stationary values are got at these points, the gradient of y equals f of x is 0 at the point 0, 2 and 2, -2. Turning points. The gradient of a curve can be 0 at several points. The shape of the curve in the immediate neighborhood of one of these points belongs to one of the 3 categories which we are going to discuss now. Moving along the curve in the positive direction of x-axis. In the neighborhood of A, the gradient changes from positive through 0 at A to negative. So A is called the maximum turning point. The y coordinate of A is called the maximum value of y, or the maximum value of f of x, where y equals to f of x. In the neighborhood of B, the gradient changes from negative through 0 at B to positive. So B is called the minimum turning point. The y coordinate of B is called a minimum value of y over the minimum value of f of x. Also note that the gradient at the maximum or minimum turning points must be 0. Also that the terms maximum and minimum values are not synonymous with greatest and least values. Maxima and minima apply to the behavior of a function in the immediate neighborhood only of its stationary values. The curve does not turn at C. That is, although the gradient is 0 at C, it does not change sign when moving through C. However, the sense in which the curve is turning does change, from clockwise to anti-clockwise. Any point on a curve at which the sense of turning changes is called a point of inflection. And apart from C, there are two other points of inflection, one between A and B, another between B and C. Thus, the gradient at a point of inflection is not necessarily 0.
Investigating the nature of stationary values. So if we consider the 3 points on the graph y equals to f of x, so A has a maximum value, and if we take 2 points on either sides of the point A, which are A1 and A2, the value of y at A1 is less than the value of y at A. And similarly, the value of y at A2 is less than the value of y at A. So both the values of y at A1 and A2 are less than the value of y at A for this maximum point A. So if we consider the minimum value, which is B, and similarly if we take 2 points on either sides of the point B, which are B1 and B2, the value of y at B1 and the value of y at B2 are both greater than the value of y at B. And now if we consider the point of inflection, which is the point C, and if we take 2 points on either sides of the point C, C1 and C2, the value of y at C1 is less than the value of y at C, but the value of y at C2 is greater than the value of y at C. So here, one point has a lesser value and the other point has a greater value. Now, if we summarize the nature of the stationary values, both the values of y on either side of stationary value for the maximum point are smaller. Both the values of y either side of stationary value of a minimum point are larger. But for the inflection, one value is smaller and the other is the larger. Now let's consider the behavior of the gradient dy by dx. For A, at A1, dy by dx is positive, and at A, dy by dx is 0. At A2, dy by dx is negative. For B, at B1, dy by dx is negative. At B, dy by dx is 0, and at B2, dy by dx is positive. For C, at C1, dy by dx is positive. At C, dy by dx is 0, and at C2, dy by dx is positive. That is, for a maximum point, the sign of dy by dx moving through the stationary value is positive at the beginning and then 0, and negative at last. For a minimum point, it's negative at the beginning and then 0, and the dy by dx is positive at the end. For inflection, there are two types. One is where both the dy by dx values are positive on either sides of the stationary value, and the other is both the dy by dx values are negative on either sides of the stationary value. So at first we considered the values of y to investigate the nature of the stationary values, and now we have considered the behavior of the gradient dy by dx, and next we are going to consider the second derivative of y with respect to x. So when passing through A, dy by dx changes from positive to negative. That is, dy by dx decreases as x increases, or the rate of increase with respect to x of dy by dx is negative. So that is, derivative of dy by dx with respect to x is negative. So this clumsy notation for the rate of increase with respect to x of dy by dx is condensed to d2y by dx2, which is known as the second derivative of y with respect to x. Similarly, when passing through B, dy by dx changes from negative to positive. that is dy by dx increases or d2y by dx2 is positive. So points of inflection are not so easily dealt with this third method. It is true to say that d2y by dx2 is 0 at such points, but d2y by dx2 can also be 0 at maxima and minima points. A more detailed analysis of points of inflection will be carried out later. So according to the third analysis, the sign of d2y by dx2 at the maximum point is negative or 0, but at the minimum point the sign of d2y by dx2 is positive or 0. So all these three methods of analyzing the nature of the stationary values are very important, and out of them the first two are the most accepted methods, as the third method fails if at a stationary value of y, d2y by dx2 is found to be 0. So in this case either of the first two methods has to be used. Now pause the video and try out this question by yourself. Okay, find the points on y equals x to the power 4 plus 4x cubed take away 6 at which the gradient is 0 and determine the nature of these points. So we are given with the equation of the graph, which is y equals x to the power 4 plus 4x cubed take away 6, and also we are asked to find the points where the gradient becomes 0, and in addition to that we have to determine the nature of the points. So if y equals to x to the power 4 plus 4x cubed take away 6, and we take it as the first equation, then dy by dx, which is the first derivative of y with respect to x, equals to 4x cubed plus 12x square, which we take as the second equation. And also the second derivative of y with respect to x equals to 12x square plus 24x. So we have learned how to differentiate the expressions with respect to x, so that we have got all these equations, and also we have got the third equation. So the gradient of the curve equals to 0 when dy by dx equals to 0. So that is when 4x cubed plus 12x square equals to 0. Now finding the roots of this equation, we get x equals to negative 3 and x equals to 0. So the gradient becomes 0 at 2 points where x equals to negative 3 and x equals to 0. So when x equals to negative 3, dy by dx equals to 0. And from the third equation, by substituting negative 3 for x, we get 12 times negative 3 to the power 2 plus 24 times negative 3 equals to 36. So we have got a value which is greater than 0. So when we get a value which is greater than 0 for d2y by dx2, by the knowledge that we have got from the explanations that this point has a minimum value, and from the equation 1, by substituting negative 3 for x, we get the y value of the particular point, so which equals to negative 33. Therefore the points with coordinates negative 3, negative 33 is a minimum turning point. Moving on to the next point where x equals to 0, dy by dx equals to 0, and the y value of that point equals to negative 6. Since the value of d2y by dx2 equals to 0 for this point, we are not able to find it out whether it is a maximum, minimum or inflection point. So in addition, let us now see what the sign of dy by dx is on either side of the point where x equals to 0. So by taking a value less than 0, which is negative 1, and substituting that in the dy by dx, we get a positive answer. So by substituting negative 1 in the equation dy by dx equals to 4x cubed plus 12x square, we get 4 times negative 1 cube plus 12 times negative 1 square, which equals to 4 times negative 1 plus 12 times 1, which is 12. So negative 4 plus 12 equals to 8, which is a positive value. So the slope is positive, and at the stationary point dy by dx equals to 0, and the slope looks like this, which is parallel to the x-axis, and when a value which is greater than 0 is substituted for x in the equation dy by dx equals to 4x cubed plus 12x squared, we get 4 times 1 cube plus 12 times 1 square, which equals to 4 plus 12, which is 16. So again we are getting a positive value, so the slope looks similar to the one which we got for -1. By combining these slopes at the point and marking the point 0, -6, we get an inflection point. So 0, -6 is a point of inflection. Now pause the video and try out this question by yourself. Sketch the curve y equals to 2x cubed plus x squared take away 4x plus 1. So finding the maximum and minimum turning points will help to give a general idea of the shape and the position of this curve. So if we take y equals to 2x cubed plus x squared take away 4x plus 1, then the first derivative of y with respect to x equals to 6x squared plus 2x take away 4. And the second derivative of y with respect to x equals to 12x plus 2. So we have already learned how to differentiate a function with respect to x. Now at the turning points, dy by dx equals to 0. So that is 6x squared plus 2x take away 4 equals to 0. By factorizing this equation, we get 3x take away 2 times x plus 1 equals to 0. And by finding the roots, we get x equals to 2/3 and x equals to -1. Which means we have two stationary values. When x equals to 2/3, dy by dx equals to 0. And by substituting x equals to 2/3 in the equation d2y by dx2 equals to 12x plus 2, we get d2y by dx2 equals to 12 times 2/3 plus 2, where we get an answer which is greater than 0. So if we get a positive value for d2y by dx2, it means this point is a minimum turning point. Now by substituting x equals to 2/3 in the equation y equals to 2x cubed plus x squared take away 4x plus 1, we get the y equivalent value of this point, which is y equals to -17/27. Therefore the point 2/3, -17/27 is a minimum turning point. So let's consider it as the first information. Now moving on to the next point, where the x value is -1, we get dy by dx equals to 0. Then by substituting x equals to -1, find out d2y by dx2. We get d2y by dx2 equals to 12 times -1 plus 2. So by simplifying, we get a value which is less than 0, which takes us to the conclusion that this point is a maximum turning point. And by substituting -1, find out the value of y, we get y equals to 4. Therefore the point -1, 4 is a maximum turning point, and we take it as the second information. As y equals to 2x cubed plus x squared take away 4x plus 1, the curve cuts the y-axis at 0, 1. So this is because to find out the point at which the curve cuts the y-axis, we substitute x equals to 0 in the equation of y. So we get y equals to 1. Or we can simply find out the intercept of the curve by finding out the value which does not have any x terms, which is plus 1. So that shows the intercept at which the curve cuts the y-axis. So we take it as the third information, and by combining all these three information, we sketch the curve as the one shown here. So we have the point at which the curve cuts the y-axis, and we have the maximum point where x equals to -1 and y equals to 4. Then we have the minimum point where x equals to 2/3, then y equals to -17/27. So this is how we analyze dy by dx and d2y by dx2 of the equation for the curve to sketch the curve. So that's it for this tutorial. I hope you enjoyed learning about stationary values, turning points, and investigating the nature of stationary values. If you liked the video, press the like button. If you have any comments, please put them in the comments below. And also subscribe to Easy Maths tutorials to get instant access to the videos. I'll see you in the next tutorial. Thank you.